Everybody. This is our further opportunity for be part of a nice event. So this is a mathematical physics seminar, and I'm here with Martin Zika, PhD candidate in our department. And I would like to say that once after reading his abstract, it popped in my mind that Martin already explained to me this, but for some reason it's kind of blurred stuff in my memory. It might reach to maybe 2 years ago past. So I'm happy, Martin, you came to explain this stuff not only to me but to you all. And I'm glad you came after all. So thanks, and the floor is yours.
Thank you for this interaction. Thank you for having me. I'll be very happy to read even a bit more, a bit further. So, talk about quantum algebras, but I want to give a simple talk and really spend most of the time talking about very simple, let's say, category theory of just linear spaces, vector spaces equipped with a category. So, our plan is to compare quantum entropy algebra structures. And we want to compare them after a certain reduction, let's say on a cosmological level. So there's a very natural physics motivation for this. A quantum entropy algebra goes a perturbative quantization of a field theory with some gauge symmetry. But I mean, you can think of Yang-Mills, for instance, but the structures and their applications also describe the double copy theory of gravity or string theory, just precisely where I think this structure was first defined by Martin Zika. Yeah. I think it was roughly 93 or something. But so for those physical, more or less physical theories, we would like to care about what predictions they give us rather than the full details of the theory. So we want to allow ourselves to reduce our theories and look at just, their effective versions. Well, and there's a very simple mathematical motivation, and that is that the recently understood reduction of a quantum entropy algebra structure to its there's sort of a minimal model on cohomology of a certain differential, which is part of the structure, is really an example of a morphism in a certain Weinstein-like symplectic category. So we'll explore this category. And for start, we can forget about most of the particular structure of a quantum entropy algebra, and just keep in mind that we'll compare some structure on A and B upon reducing them to common shared reduced subspace C. And those two areas should be some sort of natural reductions. Well, to be a little more specific, let's consider a toy model.
I ask you, as you mentioned, the physical motivation.
Yeah.
What do you mean by effective theories? I mean, concerning this thing here, what do you mean?
I'm thinking of like path integral quantization of Yang-Mills. You would have symmetry that we need to reduce. And the homological resolution of your equations of motion, the BRST complex, and then you have the anti-phase. So that would be the, let's say, the syntax part of this stuff. And this whole thing is, can be used to perturbatively quantize theories. So let's start with a third model, which will be just linear symplectic category, just category of finite dimensional with vector spaces. With a non-degenerate parent. With symplectic structure. So this omega should be non-degenerate. And anti-symmetric. Okay. Now, is my hand visible now?
Yes.
Okay, so now with this structure, we can distinguish between three types of special linear subspaces. Yeah, I need to say what Lagrangian subspaces. So, just the simplest possible version of Weinstein symplectic category. The subspace is isotropic. Is the letter I. It's contained in its orthogonal complement. Now the symbol within the orthogonal complement with respect to this pairing, and it's defined the same way you would define it for the standard Euclidean dot product, but because of the anti-symmetry, it has some different optics. Yes. So isotropic, if it contains its complement, it's like Lagrangian. It is orthogonal complement. The Lagrangian is the smallest possible equiisotropic of the largest possible isotropic. And now we can define morphisms in this category, and those will be really just Lagrangian relations as usual and sort of categories. So the subspace times V, and I put the bar here, I'll explain later, where L is Lagrangian. Bar just means we take G with the composite. That's symplectic structure. Now, the simplest example of dimorphism in this category is the graph of a linear symplectic morphism. Where phi is a linear map which is invertible and preserves the symplectic structure. And on this example, we can check that it actually is Lagrangian precisely when we add this part and we just flip one of those signs. Or an even simpler example is the diagonal subspace. It's very easy to see that we need this flip. And a perhaps more interesting example is a coisotropic reduction. So for any C coisotropic, there is a natural Lagrangian relation from, so there is a Lagrangian relation from B to C mod as orthogonal complement, and by definition, C contains its orthogonal complement, and also it's easy to read that there's an induced symplectic structure. Moreover, this relation is subjective, and essentially, like every subjective Lagrangian relation is essentially of this form. There's some isomorphism. We'll denote that by the double arrow, basically annotation for reductions. So,
Close the door.
the original philosophy of categories like this, so Weinstein's philosophy of Weinstein's categories. As a dictionary between, say, classical mechanics on phase spaces, which are grouped with symplectic structures, and quantum mechanics on Hilbert spaces. So let me just draw a little table. We will have either finite dimensional Hilbert spaces, vector spaces over C with the non-generate inner product, and category of symplectic vector spaces. And this whole table makes good sense for other symplectic categories, and most importantly the original one where the objects are symplectic manifolds. So translates from classical dynamics and manifolds to their possible quantization. Okay, so to a Hilbert space here, we assign, and this is just heuristic, this is not a function, it's just a way to think about it. In a symplectic space, we do linear dual associate this bar. So it means we take the opposite symplectic form. Now, do dense product. This is like called a direct product, but dense product. We assign a Euclidean product. So really, we should think of we should think of the Euclidean product as a monoidal structure. Now to a linear map here. Quantum operator, we could say we assign, of course, our morphism and our categories and Lagrangian. And right of the target and the source and target. And okay, let me add that to the Hermitian conjugate. We can assign the transpose of a relation, and that's a very simple thing. We just understand L, the subset of E times V, as a subset of V times U. And yes, what's going on down here? Yeah, a bit more abstractly, there's a both dagger compact categories. And this kind of categories have been described by Abramsky. And it was 2003 as categorical semantics for quantum theory. So they should provide a good abstraction of how a finite-dimensional quantum mechanical system behaves.
May I ask?
Yeah.
So you mentioned you have two categories of some kind, and what's the relation between them? You just compare objects themselves, but you don't have any functoriality imposed.
So the relationship is that both are dagger compact in the sense that a dagger compact category comes with a dagger and a dual. And the dagger is here is the permission conjugate, and here is transpose, so that it's supposed to mirror the permission conjugate. And the dual is the later dual or the flip.
Yeah, but you sorry.
And they're just supposed to have some properties, have some compatibility properties. For instance, the dual, we should be able to use the dual to define internal harmonics kind of. So yeah, so it's really both our dagger compact categories, and those are daggers for the duals.
Yeah, so any preservation of compositions and stuff.
No, I here I don't think there's any sort of point of it in this.
Okay.
Just come back to me again. Oh, it's just I think it comes from there's like a series of definitions, and it's like one of the several words in one of those definitions along the way. Basically, just the dagger should be registered involution, and well, the dagger and the dual should be compatible with the monoid structure in the category. That's one part of the very compact categories as well. So yeah, compact comes from compact closed, and I don't recall which one of those properties, but it was one of those three natural compatibility conditions between the dagger, the dual, and the monoid structure. And maybe in general, like the rating of the category should be compatible.
And the dagger is just a name of a functor.
Yeah. Okay.
Or there will be some functor quantization and classical maybe. Oh, the functor in the optimal world would be maybe quantization and classical.
Yeah, like from Elvis space.
If you could make precise window.
All right.
I did the identity of the object.
So
Dagger is identity of objects.
What is dagger?
Yeah, yeah.
Does it change?
Yeah.
Oh,
Abramski, okay. COEC. Okay, so now let's look at how what a generic Lagrangian relation looks like. I guess a proposition. Every Lagrangian relation.
Really, you don't want to take an extension where you can actually have normal composition correspondences.
Yeah,
Relations, and then you can like use methods of like Woodward and
well, in for now, I mean, for the whole program, we're just working with vector spaces, so there's no transversality problems. There will be some other problems. So it's still, so the Wareham Woodward idea is something we're working on right now, but for different reasons. So every Lagrangian relation factorizes as follows. So let's take a Lagrangian relation L. We can draw a picture like this. Just draw it and describe it. Okay, so first of all, we can always take transpose of any relation, and the image and the kernel of the transpose are often or usually non-trivial. And moreover, the image of any Lagrangian relation is coisotropic, and the kernel of transpose is its orthogonal conformation. So it makes sense to take those factor spaces and they come with an induced symplectic structure. And moreover, we can find this arrows, those Lagrangian relations, where this one is sort of LU, and this one is a reduction. So with a draw a double arrow. This one is injective, so we'll call it a co-reduction. You just draw a arrow like this, and this one is just an isomorphism.
Maybe Martin can tell us what image is.
Yeah. I mean, okay. Image is just all these elements of the target which are related to something, and the image of the transpose are all the elements of U which are related to something. Kernel are all those elements which are related to 0. Kernel of transpose are all those elements here which are related to 0. So it's really just what you would expect from a map, but here we have relations which are maps with let's say a small domain of definition and possibly some indeterminacy, which is the kernel of the transpose. So you can assign to one element here multiple elements here by a relation. Okay. So as a consequence of this, there is a flip this arrow. If you flip an inductive relation, reduction, correction, we get a reduction. So there is a factorization goes down. That would be a picture of this. We forget about its isomorphism, or let's say, put it inside one of those other arrows. We have a way to take any Lagrange relation and assign to it pair of projections like this. So that's the picture we have in the figure. That's the action from which we want to reduce our structure. So go to compare them down here.
So if you only do invert the arrow, right?
I think just to transpose. So I just understand it as going in the other direction, and that's it. That's it. The defining property is that this holds. It's a factorization. If I flip it, then L. Okay, this should have the name LB transpose. Okay, and as a consequence, it's a theorem. There is an equivalence of categories between our linear symplectic category and the category of response projections. So if you have a traffic relation, you can assign a corresponding projections. It's unique up to the choice of this R. So there's some isomorphism class, and vice versa. If we have a constant, we can just flip this one, compose them, and we get a Lagrangian relation. Also, from this factorization property, we can define composition of constants. Moreover, if say L1, L2 do Lagrangian relations, let's say they go like this. L1, L2. If they compose orthogonally, I'm returning that the image of L1 here and the image of L2 transpose or orthogonal. Then the composition of corresponds that we get from basically how Lagrangian relations composed coincides with a classical junction of composition of corresponds, that is to compose them along two shapes. Let me draw a picture. We have three corresponds like this. So maybe they came from L1 and L2. Well, then if L1 and L2 compose orthogonally, there exists a pre-shot of this diagram. And actually, the pre-shot exists precisely when this holds. Yes.
So let us correspond. Yes, I was wondering, so does this correspond reduction category also inherits the dagger structure?
Sorry.
Does this correspond reduction category also inherits the dagger structure? So this is equivalent.
Yeah. I mean, okay, let me think about this. It's sort of okay. It's actually sort of trivial because I mean, yes, but it's just about like which one you consider the first. The second, there's not very much happening, but then again, not really much is happening for the relation. You just understand something is so yeah.
So the biggest fraction right exactly wasn't about the notation of the factors in here.
Yeah.
Okay.
Right, so it's quite simply just a not a fun fact, but it will not quite useful. So just
And is it general through that epimorphisms are preserved by pushouts? I'm not really sure about this.
that I don't know. I don't
It
but
should be some categorical property, but I don't think this property regard to co-limits, not limits.
okay, so now it was okay. One thing I didn't see much properly.
It's epimorphism in this category, so it is subjective map or some cohesotropic manifold.
Yeah, I think that reductions are precisely
Exactly.
circumorphisms.
Yes.
And here, okay, there's a good point. I didn't specify. I say push out here. I mean push out in the category of reductions. So let's say just the category of epimorphisms. Okay, so it's not about whether push out, because push outs don't exist in this linear symplectic category. But if we only take reductions and this condition of orthogonality between, let's say, somewhere in here,
Okay.
then in the subcategory of just the reductions, the push out exists. So it's basically this category has very, very few limits and colimits. And one of the reasons is that there's a dagger, and the dagger, the dagger would basically make every limit into a colimit of the same diagram. So whenever there is a limit or a colimit in this category, it's also the other thing. So that's super strong. So there aren't many limits or colimits. So this is a very special thing that we need to go to the subcategory of just reductions and have this condition. One last thing, just a short remark about the soy example. Right, so let's compare, let's try to look at coisotropic relations, because a Lagrangian relation, a Lagrangian subspace is always a coisotropic subspace. So coisotropic relations should generalize Lagrangian relations. Okay, so let's denote this quotient RC, or this one being coisotropic. Like remember, we have always this, this symplectic space, and that's a reduction from the original symplectic space to this quotient. And we can form a, there's a well-defined notion of category of coisotropic relations with everything defined the same way. And relations will be, again, subspaces of the product, which are coisotropic, composition, everything is the same. But now there's some new structure which sort of, bears witness to the fact that this is more general than Lagrangian relations. it's a Lagrangian relation, special Lagrangian relation. For any pair of Wise-specific relations that are next to one after the other. And it's related by X. And it goes from RC to prime to composition. And there's a very natural definition. You just escape the obvious definition of relations and then put the coordinates everywhere. And I think I just want to say here, that also plays a role in quantum algebras, is that this thing, this natural sort of reduced composition thing, turns out to be something that people call a compositor. And that is, a compositor is a coherence datum of a certain two function. And yeah, here. So it's a compositor of R, this very simple, operation that goes into reduction, because it can be interpreted as a two function. As a large two function. And it goes from category of Wise-specific relations to one object category associated to the linear symplectic category. Say model categories again associated to a one object category. This might look strange, but it's very simple. Here we understand, here let's say on level 0, it takes any space here, any symplectic space here to a single object. On level 1, it sends a coisotrope to RC. So that's the original meaning of this. On two cells, it just sends we extend this category. This one category, we just identity two cells. So it sends just the identity to the identity here. But that's not the whole story, because this, this U functor comes with another piece of data that's its compositor, which describes how composition works, and that compositor takes values in two cells here. Two cells here are the one cells here, so Lagrangian relations, and this is a Lagrangian relation. So this is just a way to compare quasi-tropic relations and Lagrangian relations, and there's a way to value structure. And yeah, it's going to be also interpreted for quantum algebras. So I think it's time to sketch just the basic idea of how this category theory of symplectic wave spaces works in context of quantum algebras, what the roles of those operations and constructions are. So first, a DG symplectic space will be a vector space, just as we had it a finite dimensional real vector space, but now we want it to be z-graded. Still finite dimensional, but z-graded. Still have the same symplectic billion form, but now we require it to degree -1. So switches changes the degree, and that means that it only pairs two homogeneous elements non-trivially if their difference of their degrees is 1. And the reason for this is that this provides a nice compatibility condition with a differential, say, differential. Of degree 1. This is how it sort of appears in this generated. The symplectic structure is made to sort of work with the differential, and for us it would actually be useful to instead work with a quadratic function. We call it S3. And in terms of a pattern Blokowiecki theory, it would be the free part of a classical master action. It's quadratic in the sense that quadratic in elements of V star. And this function is a special case of formal functions on which we have, let's say, big polynomials or even formal series in powers of elements of V star. And okay, this thing we can produce it using the symplectic form, and for this to be a differential or correspond to a differential, it should say something like this. A bit back here, say that divergence, some sort of symplectic divergence of this exponential should vanish. And so if you know, if we're familiar with this, and this symplectic divergence is just the Butterman-Minkowski question, say divergence operator, which is induced precisely when the degree of the symplectic form is odd. Nothing like this exists in the even case. Well,
Martin, what does it mean this F? What does it denote?
yeah, it denotes say completion of a space of symmetric powers of V star. So I take just powers of V star, tensor powers of V star, and then I take so I don't know to form a series. So from
result of
No. H adding.
completion is in vector space.
Yeah.
yeah, I mean that does show some way to understand as a topological completion. So just form a series. Yeah. A little technical.
If you think, for example, that your VIs, so here you assume that all VIs are finite dimension.
Yes. That's
So since you're talking about the dual, for
Yeah.
example, they use
It's degree by
and in fact this thing call it the -1s in fact category linear, and everything I said works for this category as well. And in fact, if we just say the VI's finite dimensional, but possibly if there are many of them, it still works. But for the rest, what we're gonna do, we need this to be finite dimensional. So right.
Таким картин degree.
Okay. So the important thing about this structure is that this uses a well-defined, say, abstract notion of integration, and that's what we're looking for to integrate complementary structures to their effective versions. So let's say there is an axiomatic or an abstract Gaussian integration. Gaussian integration map along a reduction if we use an integrability condition, and that's a very simple one. If this quadratic, if this quadratic element is non-degenerate on kernel of F. Why is it quite specific? That's because our integrals will be, and we want it to be, over this stuff we want to get rid of in proportion like this, so that restrict on required isotrope and integrate of the complement, the isotrope. That's the law of kernel of L here, and we weight the integral with our S3. Yes. So I'm also writing this H bar here and here, and here in physics here, that doesn't surprise you. If you don't, it's just for us, it's just a formal parameter which helps us keep track of what really it's as a new sort of grading. Yeah, which helps us just organize our operating for taking. And this thing, let's say it goes from F on U to F on R. And it doesn't then detail that in fact it should go from half densities in U. So functions that also transform with a square root of the determinant, or in this case, the Parisinian. Then using some properties of this constant vector form, we can actually make this work and transform like a real integral. So from a half density on U, we can create a density on the kernel. We use it to integrate. We're left with a half density here. This is a really important detail, but it's a detail that we can yeah, skip for the rest. So almost finishing now.
You don't need a complex structure to integrate over the kernel.
No, no. I mean, here it's just vector spaces first. So and this okay. So while I raising the blackboard, I can say a bit more about this slightly esoteric theorem. So what does it mean that there is an axiomatic Gaussian integral? That's something I haven't explained. And
Maybe put minus before s. Before the exponential minus.
Yeah, I could, and then it's. The thing is that we can define this integral by a few axioms, by 3 axioms, and it's really just let's say sort of a version of a Stokes theorem. It's a natural normalization, and let's say compatibility with this S3, which is our differential, or integrals are differential, and that also ensures it really behaves like a Gaussian integral. So what we are aiming for is to use the very simple algebraic properties of Gaussian integrals. In particular, it's quite easy from those axioms to prove a version of the Weight's lemma. So the Weight's lemma, if you know physics, we have used it to construct Feynman diagrams, and yeah, it's just a way to see that this quadratic thing really just contracts pairs of elements together. And yeah, so this is one of the main motivations. It's very easy to prove that the Weight's lemma holds. And the motivation for this axiomatic definition really comes from the homological perturbation lemma, because it's really the way you can characterize this map by a set of 3 or 4 axioms is precisely because it's a special case of something reduced from or by the homological perturbation lemma, and by using the properties of the homological perturbation lemma, we can see that those properties, those axioms are. That's what behind it. Homological perturbation lemma is hidden inside. Or if you're a physicist, it's Weight's lemma and Feynman diagrams. If you're a mathematician, it's homological perturbation. Okay, so I'll just take a quantum element in the algebra. Formal function. So S this would be actions. So this would be Button Volkovitsky formulas, and this would be the quantum master action. Again, it's enough to assume that this symplectic divergence is exponential. So quantum monofinity algebra is really the structure of a DG symplectic space together with this special formal function. And now you may know Algebras algebras or other homotopy algebras as a collection of possibly an infinite amount of let's say brackets or morphisms that generalize the algebras and associative algebras and so on. And this is the same thing, but here let's say that the structure coefficients of those higher maps, those higher morphisms, say higher brackets, are encoded as coefficients of this formal function as a formal series, and in powers of elements of V stars, or powers of, let's say, coordinates, and so this is where these high brackets or high morphisms are hidden. And this quantum really just means that there's this symplectic divergence. It means that it comes from the fact that it appears when we're trying to calculate quantum path integrals with other local, and for that we're using precisely this symplectic divergence. So it's really just an element in the algebra sort of represented by this operator. Okay, so now we can say what the with getting to the title of the talk. So let's say that the partial category on the element in the algebras. Those structures as objects or somebody spaces with those functions as objects. And so the quadratic relations. So as a Lagrange relation. Isomorphism.
What is the bracket?
Partial.
Okay.
Partial. I can make it better. Make it a bit worse.
So you understand it well that this bosonic space, I mean FV, has already a different Lie algebra structure, or like a commutator of endomorphisms? No, I can deform it already, or it is really Lie algebra. It can be really Lie algebra.
I mean this well the which one? This space of F with Lie algebra defined by what? By
Commutator.
uh
I need maybe duality, but
well it's symmetric. It's by definition it's symmetric, so everything that matters on these remains with a sign. So just the commutator doesn't give much.
so the associator. I mean, the difference of commutator.
Well, that would be, yeah, that would be either zero or we give just sign differences.
It'll be the trivial.
So and all the
Okay.
structure is here comes from those formal functions. So it has a Lagrange relation as a morphism. Okay. Now let's probably factorization goes on. We know that there's a U of a reduction here. You know it from the first part, and second a relation is a morphism of elephant algebras. Let's say S here is prime here, and we will rewrite S is related to prime by L if the integrals of those two structures along those reductions going integrating over the kernel value and this things only there's something that's maybe there's maybe isomorphism is the property and there's some half density missing, but that's they actually just integrating over exponentials of S.
The reflexive or symmetric.
Well, it's definitely yeah. It's I mean it's reflexive because you can always take the identity and the integral over the identity is just identity. It's symmetric definitely. That's part of the let's say dagger structure, and the question is it maybe transitive as well, and that's where the partial comes in. It's not a category, and let's get this proposition.
So there should be S prime.
Yes.
Thanks. Thank you. So That's S is related to S prime. O1, O2. So let's assume this holds. And it's not automatic that S is related to S double prime. But also L1 and L2 compose organally. Then that's so S is related to S double prime by L2 composed with L1. So just recall that this orthogonal composition and that the image is sort of met in an orthogonal way in this sort of picture. And this allows us to take a push out here. So the important thing is that we have a commutative square of reductions here, and the idea is that integrating all the way down defines a unique, well-defined reduced fundamental structure down here. So in order to do this, in a consistent way, we need this thing, and we need to, let's say, compose along the channels. Right. So that's it. That's the well, not really a category, but a partial category of fundamental algebras. And
Only morphism in this category is an isomorphism.
yeah, so in this category, yeah, I mean it's okay, let me yeah, basically, yeah. But it's really sort of like it's almost an equivalence relation, but with partial composition. Now, so do I have any time left, or
I don't know.
When did we start?
It depends how much time. We started about 2 minutes after 14. So you can add some final remarks if you wish.
Okay, so I will just add a final remark here. Take a minute. Yeah, I won't say too much. Just say that yeah, this idea here, the use of this is that we can there's a way to think about a quantum allocated algebra structure on V as a morphism from a point to V. But this morphism is a quasi-topic relation between this and this. And in particular, it's the whole space V. And then we also equip this quasi-topic relation with some other data. We equip it with, let's say, this S3 part. And this next one. So transformer function on the quasi-topic reduction on RC. If C is the whole vector space, then it has no polygon complement, so the reduction is the whole space. So we have, so it's really just this S3 and a function on the whole space. And if we then take, let's say, a Lagrangian relation here, that's also a quasi-topic relation, but again, a very special one is if we take the reduction, we're left with just the zero space, with the point. So here we have a quasi-topic relation together with data on this reduction, but there's nothing here. There's like the zero. Let's say that is also zero or one. There's nothing. So there's a way to generalize this stuff. Generalize Lagrangian relations, quasi-topic relations, together with some data on their on the reduced spaces, And that way we can think of the objects, the quantum the algebras, and their morphism, Lagrangian relations, as just morphisms in a certain category. And then we can just, or let's say, if two different quantum unpaired algebras, we can say that a relation of those quantum unpaired algebras is really a diagram of this shape. So really, let's say it would be it's more of a motto than like a random, let's say, just relation of quantum infinity algebras is something that lives in cospan. It's this cospan, and in a comma category, under category, under this point. So objects are those guys, and morphisms will then be the triangles. So and this category, let's call it generalized plane. This one. We love this generalized Lagrangian relations, which are for isotopic relations with some extra structure of the reaction. And yeah, and so it's really just sort of picture and this two factor can be extended to this setting and yeah, I mean if you I can write the two factor and it looks like it's a different version of it. It's just taking that thing, taking the quadratic reduction, which can be restated as a very simple like function. You can add all this data of quadratic stuff with defines integration and this structure of a quantum algebra, and you can still extend this two function. And so I just say different ways to look at it, different way to look at it as in terms of a certain common category. Yeah, but that's just like slightly. This is going to be the important thing. Okay, so that's all the whole picture I'm going to do. Joe,
Thank you very much. So I hope there is some time for your questions.
So going back to the category in C, the dagger structure. Yeah, as you mentioned, because of the dagger structure, there are few limits and polynomials.
Yeah.
So I was wondering if the definition of this category. I was thinking that at the level of objects, we not allow infinite dimensional vector spaces. We just mean probably the definition of symplectic structure can be adopted. But I was wondering if the morphisms are tricky, if there are any subtleties defining Lagrangian submanifolds, if the Lagrangian subspaces in this case, in the infinite dimensional case.
Oh yeah, not good. I was trying to see if there's something, just like a simple way to just practical completion of this, but I haven't really found anything, and so really, I just ended up with what we need, and what we did wasn't really all the limits and colimits and going to something bigger, but really just well the opposite thing, just right. I was to take the subcategory of reductions of endomorphisms and work with that. So no, I don't know how time still completion really case.
That's an interesting category because since everything has an underlying linear structure, so any abstract categorical statement becomes a statement in terms of vector spaces and systems of linear equations.
Yeah.
So for example, we can check Leonard's lemma. and then say something about invariance of objectives and
These completions are handled extensively by Gishadet, somebody called Gishadet, after the forms remembered Gishadet, Guib, CHAD.
Yeah, that does seem to be well.
Okay, any other question?
I don't know. What happens if you add at least a bit of geometries?
Yeah.
If you get from vector space to some very, very basic simple.
Yeah, so a lot of this, so the DG cinematic, this part, that.
Let's say you take S2.
Okay.
It's the simplest possible.
Okay. Well, so S2 would be the even part and the odd part.
Take places.
Yeah, I mean, but without the infinity thing, just the DG symplectic space, that's been done by Schwarz. So this really, so I think that most of this should work. It should be, should with some transversality conditions and so on. It should be possible to extend it. Yeah, this whole thing, integration and half densities now going to a blind bundle of half densities, and a lot of the things here actually make a bit more sense. It's like the business with half densities is here. It's not just numbers, just normalizations of translation invariant measures. So that makes a bit more sense. And this divergence, the Button-Volkovitsky operator, also makes sense as well. Comes from a Lie derivative of hard densities. So a lot of it translates naturally. And for the things I'm not sure about, we try to I forgot to say this is both things. It's still work in progress. With Banyocho and Pullman, and basically trying to make the fact that we're trying to make things categorical and universal is also because we hope that then it might be easier to extend it to maybe some geometry or to add a bit of geometry. So yeah, so this thing is done, and the rest hopefully with similar universal constructions. Yeah, I'm not sure. I haven't really done anything about like quantum and infinity algebroids. So that's like that seems like there might be technical difficulties with that, but the rest of it, it goes by the name of PQ manifolds.
Expect to see some sort of a almost equivalence relation as well with proposition if you have like a bit of geometry. So
Yeah,
it's
yeah.
kind of difficult to imagine.
Yeah. So actually, this one thing we're not that sure about, but the same way we can work around transversality, the problems with the Varham Woodward category. Something similar should work here, or might work here as well. If we're able to take some sort of pullbacks, and they don't really exist in those categories, but thinking of both ways to do. There's a lot of structure, so in some ways, I think it should be possible to build nice pullbacks and to make them orthogonal automatically. So in that way, we could maybe work around this orthogonality condition. So, so maybe if this works, then you know, it's something that could so both of those things. This this condition is really this orthogonality condition is basically, I think it's basically the same thing that appears in theory of zero foliations and Boston geometry. I think something in very similar condition appears in Morita equivalences. And yeah, and I think was it? I think in Vincenzo's talk there was once some sort of a condition on it remind me of this very much. It was like in the kinds of foliations, right?
It's basically that, very difficult.
Yeah. So yes, this doesn't mean
It's known that once you pass from this category to derived cases, all the issues concerning non-existence of push-outs disappear. So is it your aim to go this way?
it might be. I mean, it's sort of it's sort of in this direction. We're trying to work with, you know, with like morphisms that basically it's like the minimum model is for the vacuum mutate cohomology.
Yeah.
So this whole thing really is sort of working on the level of cohomology or making category which works nicely. We can do that to cohomological level. So I guess it's tempting, but I'm not sure.
If I recall it correctly, this morphism you constructed or you spoke about has something to do with weak equivalences between these two approaches, between infinity algebras, but not quantum infinity algebra. So I wonder why you haven't mentioned the same story or the same thing in the story of infinity.
So your what morphism are you?
So once you consider this reduction and ask whether S free is a non-degenerate on kernel, you can ask the very same question for obtaining the morphism between infinity algebras.
Okay.
Somehow.
Okay. So just integrating.
Yeah.
Elemented,
in general, replace just S3 with the S.
Well, here S3 is just plays the role of of the Gaussian part, and I mean we replace S3 with S here. So yeah, that's exactly what we're doing here with the quantum structure, where the S3 is part of S, so you can still use Wick's lemma and Gaussian integration, and there's the rest of the, let's say, the interaction part in here. For L infinity, I mean the thing is that the defining property, in physical terms, really means that let's say path integrals or like integrals with this weight. So that means that would be mean values of observables are gauge invariant. So really, the definition, this kind of definition of the quantum element algebra means that it's well suited for integration. And that's the quantum. The quantum is really just this, odd symplectic divergence, the big Laplacian.
Okay.
And it means that this integral, or an observable here, it's getting very nice. So I think it will just break down if we don't have the compatibility with this.
Okay. Maybe have one final comment on my question. I just persuaded myself that my former question concerning the properties of morphisms you getting out of pushouts are really effective epimorphism. It's a part of categorical properties of these collimates. So don't worry about it.
Okay.
So, is there any other question? If not the case, I would like to thank you again, Martin. Next time there will be no seminar, apparently, I guess.
No.
But do we have
Yes.
somebody?
Unite, I guess. Unite.
Okay. So we will get to know in the right time what is the topic. But the next time, or I mean next week, there will be no such seminar. Thanks for taking part. Bye-bye.